My name is Callum McCreary, and in this talk, I'm going to be discussing a paper with Will Mon. So before I talk about the focus of the paper, which is on a randomized rounding tool known as a contention resolution scheme, I first want to motivate it via a problem known as the profit matching problem. So in the profit matching problem, one's given a graph G with a collection of known distributions describing the graph's edge weights. And for simplicity, this is going to be done via the product distribution. So the goal of this problem is that I want to output a matching of the graph G of large expected weight. Now, the reason it's interesting is that initially the instantiations of these edge weights is initially unknown to the algorithm. So instead, they're revealed sequentially, where in each step a vertex arrives, and the algorithm then learns the incident edge weights to V. So at this point, it makes an irrevocable decision as to whether or not it wants to match V. In this problem, the algorithm competes against the expected weight of an optimum matching. And in the profit inequality matching problem, the arrival order is generated by an adversary, whereas in the profit secretary matching problem, the arrival order is uniformly at random. So the secretary matching problem is easier for the algorithm as it gets to average over all the possible arrival orders. Okay, so one popular approach for designing a profit matching algorithm is as follows. There's first an offline step where, using the known distributions, one computes the probability that the offline benchmark matches any particular edge E. So what one can observe is that after computing these edge values, they actually form a fractional matching. In other words, if I fix any particular vertex and sum up the incident fractional values, then the sum is at most 1. The second step is the online step. And the goal of the second step is that, okay, once I actually have this fractional matching, I want to turn it into an integral matching, so I actually get an algorithm for this profit matching problem. And the way this randomized rounding is done is precisely via online contention resolution. Okay, so how does an online contention resolution scheme work? Well, an OCRS is given a graph G together with a fractional matching. In each step, a vertex arrives, and it draws a previously arrived vertex with probability XUV. So clearly, when the first vertex arrives, there's actually nothing that arrived prior to it, so you can interpret this round as simply just a pass. In general, I now move to, say, the second vertex, V2, and now I flip a new coin, and it happens to be the case that V2 selects V1. So at this point, when V1 is chosen by V2, we refer to the edge as being active. So clearly, every edge of the graph is active with probability XE, and there's also negative correlation, meaning that there's at most 1 active edge per vertex. So when the OCRS learns of an active edge, so in the picture here, it learns that edge V1, V2 is active, it then has to make an irrevocable decision on whether to add this active edge to its matching. So you can imagine the process continuing step by step. I learned that edge V1, V3 is active. However, I can't add it because I already matched V1 to V2. I go to vertex V4, a random draw occurs, but it doesn't happen to select a vertex before it, so we interpret this as skipping the round. And finally, I get to vertex V5. Edge V3, V5 is drawn, so I refer to this edge as active, and in this case, the OCRS actually adds it to the matching. Good. So the goal of an OCRS is the following. It's a universal guarantee with the property that if you fix any edge of the graph, then the probability that's matched, given that the edge is active, is at least some alpha constant for alpha as large as possible. So if the arrival order of the vertices is adversarial, then we call it an OCRS. And if the arrival order is uniformly at random, then we refer to it as an RCRS. So again, this guarantee that I've written here is actually easier to attain, i.e. we can get better alpha values provided we're designing an RCRS opposed to an OCRS. Good. And so for the analysis in this talk, it's going to be convenient to use a trick from sort of the online matching literature, where instead of working with a random permutation for the arrival order of the vertices, we'll think of every vertex as having a random timestamp, which we'll call its arrival time. And this is just going to be a independent and uniformly at random value from the unit interval. And once we have all these timestamps, we then just think of the vertices as arriving in increasing order of these YV values. Good. Okay, so why are OCRS and RCRS important? Well, the nice thing is that they actually provide a lossless reduction to the profit inequality and secretary problems. In other words, if you give me an alpha selectable OCRS, then one can use it to design an alpha competitive algorithm for profit inequality matching. And the same reduction is true for RCRS and profit secretary. Good. That being said, the applications of OCRS and RCRS, they actually extend beyond profit inequalities, and they really become sort of a general tool in stochastic optimization. So just to list a couple of additional problems that these tools are useful in. So the one example is this query commit matching problem. There's also this price of information matching problem. And there's a more surprising application in the stochastic matching with few queries, where these RCRS are used in an interesting way. Okay, so the focus of this talk, however, is going to be to derive improved upper and lower bounds on the selectability of an RCRS. So the selectability is going to be defined as the optimum alpha that one can attain. And here we'll think of lower bounds as being positive results, i.e. they're algorithmic, and upper bounds as being negative results, so impossibility results. Good. So just to first discuss the past results in the literature, Ezra et al. Showed that for OCRS, half is attainable, and this is actually best possible. For RCRS, Fu et al. Showed that you can actually beat a half if you assume random order vertex arrivals, and they showed that you could actually attain 8/15, which is about 533. They also showed an upper bound of roughly 0.567 that holds for general graphs. So the main result of our work is that we show that if I restrict my attention to bipartite graphs with two-sided random order arrivals, then we can match this upper bound of Fu et al. So we can actually also we can get an algorithmic lower bound of 567. So the nice thing here, though, is that instead of, if we just look at graphs that have odd girth, so meaning the shortest odd length cycle is, say, lower bounded by G, then we can actually generalize this positive result, and we get asymptotic convergence to this 567 value as G tends to infinity. The sort of surprising thing here is that the convergence is very rapid. So you can imagine if the graph is triangle 3, this is like the first non-trivial kind of value for working with odd girth. And if I make this sort of minimal assumption, then I already get a lower bound of the selectability of 563. Our other results are a complementary negative result for bipartite graphs. So we show that the actual optimum selectability value for RCRS and bipartite graphs is upper bounded by 567. So in that sense, combined with our first positive result, we resolve the optimum selectability for bipartite graphs. And the way we prove this is that we analyze an online matching algorithm on the complete bipartite graph with uniform edge values. The main idea is that we show that for a typical random arrival order, no more than 0.567 n of the edges can be matched as n tends to infinity. Our final result is for general graphs, and here we design a different algorithm that attains 0.535 selectability guarantee. So it's a slight improvement on the Fu et al. Result. But the interesting thing here is that to get this result, we actually run sort of a hybrid algorithm, where we initially run the half selectable Ezra et al. OCRS, and then once we do that for a while, we finish the process by executing the greedy RCRS of Fu et al. And what we show is that if you interpolate between both these algorithms, then you get a better guarantee than either one can achieve alone. Good. Okay, so the remainder of the talk, I'm going to be focused on the techniques that we use in our main result, so our positive result for bipartite graphs. And in order to describe this, I want to introduce a bit of terminology. So first, if I'm looking at an edge E, I'm going to define its arrival time to be the max of the vertices arrival times. Okay, good. So the way previous RCRS work is as follows. They first compute some sort of explicit function that depends on any particular edge E. And then when an edge arrives and it's active, it gets accepted with probability f of E applied to its arrival time. So for example, Fu et al. Use an explicit function that depends solely on each edge's edge value. But other works have also focused on these sort of functions that also take into account the arrival time of the edge. Okay, so the main observation is that when working with these types of RCRS, we can write out the selection guarantee as a function of f, as well as the probability that the edge is actually feasible at a specific time. And so all the work here is done on lower bounding this the probability that an edge is feasible given its arrival time as well. Okay, so how does our approach differ? Well, our approach is recursive. So let's imagine for a second that we've defined an RCRS up until some time y. And now we want to extend its definition to any active edge which arrives at time exactly y. So first, what we'll do is we'll write down what we're going to call a selection function. And the way you should think of a selection function is it's going to be the target rate that we wish to select an edge that arrives at time y. Okay, now since the RCRS has been defined strictly before time y, we can actually write down the probability that the edge is feasible at time y given the arrival time of E. Because of this, if we now set our function f to be c of y normalized by this conditional probability, then based on the equation from the previous page, we get an explicit expression for the selection guarantee attained by our RCRS. Okay, well, when is this approach actually well defined? We need to ensure that this function f is upper bounded by 1. In other words, we need to lower bound the probability an edge is feasible by this function c. And the way we do this is via a technique called continuous induction. Okay, so how does this continuous induction approach work? Well, let's imagine we fix some time y, and now we'll make the induction hypothesis that for any edge f that arrives before time y, I can write down the explicit probability that the edge is matched as a function of c. And now my goal is that, okay, if I now look at some edge that arrives at time y, let's assume without loss of generality that u comes before v. And then what we observe is that, okay, the edge is going to be feasible to be matched at time y if and only if its first endpoint, so u, was not matched before time y. In other words, we need to show the following lower bound on this conditional probability. Now, the way to think about this, so the sort of part of the argument, is that we need to show that, okay, if we assume the edges were selected before time y correctly, then we need to ensure that this conditional probability of u being available is not too small. Okay, so how does this go? Well, first what we can observe is that just by flipping around the probabilities, it'll be easier to think about upper bounding the probability that a vertex u was matched before time y. Now, the first step of the argument is we actually want to get rid of the conditioning on the arrival time of v. So how do we do this? Well, what we observe, and this is where we really make use of the fact that the graph is bipartite, is that we prove the following upper bound. So on the left-hand side, we have, we're conditioning on both the arrival time of u as well as v. And on the right-hand side, we're only conditioning on the arrival time of u. So what we can observe is that the right-hand side averages over the arrival time of y of v. And you can think about it for a second, but effectively it only differs from the left-hand side when y of v comes before time y. And so it suffices to focus on this case. So let's imagine a possible sort of sample path execution of the right-hand side. So here both u and v are coming before time y. And we can imagine that there's this even length cycle that exists between u and v. So the blue edges here are active, and the arrival order is u, v1, v2, v. Good. So because of this arrival order and the fact that all of these edges are matched, what happens is that as the RCRS executes, it ends up adding the edges v, v2, as well as v1, u. And so the point is that in this execution, so this orange execution, v actually helps vertex u get matched because it blocks the edge v1, v2 from having appeared in the matching. Okay, if we now look at the left-hand side execution, so the way to think about this is that if I condition on v arriving at time y, then it's as if I actually took v out of the picture. Okay? And that's because this event here, i.e. u is matched before time y, it doesn't depend on what happens at time precisely y. Good. And so what you can see here is once I remove v from the picture, this blocking event no longer occurs, and the RCRS ends up adding the edge v1, v2, which then causes u to no longer be matched. So in this sense, you can see in these sort of sample paths that the removal of v can only actually hurt u from the perspective of being matched. Okay, so the second step of the analysis is actually applying our induction hypothesis to this conditional probability where we've now removed the arrival time of v. And the way this goes is as follows. So you can imagine I want to write out the exact probability that u is matched before time y. And the way I do this is I look at every vertex w that's incident to u, and I ask for the following three events to occur. Okay, I definitely want w to arrive before time y. I also need the edge u, w to be active. And finally, provided both these events occur, I need to ask, okay, what's the actual probability that this edge u, w was matched by the RCRS? And here, I won't go quite into all the details of how we derive this next step, but the idea is here we just apply our induction hypothesis, which we can do because both u and v arrive before time y. To now get to the next step, we use the fractional matching constraint applied to u, and we get the following upper bound on the probability that u is matched before time y. Okay, so putting everything together, i.e. applying steps 1 and 2, we get the following explicit lower bound on the probability that u wasn't matched before time y. And so recalling the initial goal, this leads to the following integral inequality. It leads to a constraint that C needs to satisfy in order for this RCRS to be well-defined. So if we solve for this integral inequality, then we get the following explicit function. And what this is saying is that, okay, if we actually take C to be this function by definition, the inductive step is going to, we can actually complete it. And so what it means is that the RCRS is well defined and we get the desired selection guarantee. Okay, so just a quick disclaimer. Since we actually want our RCRS to be efficient, our formal proof actually discretizes the unit interval and actually applies like a regular sort of inductive argument. But all these sort of important ideas are more easily seen in this sort of continuous setting. Okay. I now will just talk briefly about how this result sort of adapts to this odd girth setting. And so the main idea is that step 2 is actually the exact same. However, step 1 changes slightly. And the idea is that, okay, since the graph is no longer bipartite, there can be some odd cycles in the graph. And so previously we just had an upper bound of 0 here, i.e. we upper bounded this probability here by the probability where we take away the conditioning on V. However, when there do exist odd length cycles, we can no longer do this. We can, however, say that, okay, if U is matched when V is removed from the picture, i.e. when vertex V arrives at time Y, then there had to have been this sort of rare odd length cycle, which includes the edge UV. And so by actually upper bounding the probability that such a rare cycle exists, we get this term on the right-hand side. So this, of course, leads to a new integral equation. However, the nice thing is that there's still a closed form solution, and we can quickly see that we get very nice convergence towards this optimum selection guarantee. So for instance, when G is at least 5, i.e. the graph is triangle free, we already get a selection guarantee of 5, 6, 3. Okay, so I'm just going to conclude with a couple of open problems. So of course, the most natural thing to ask is, okay, can we actually extend this 0.567 result to general graphs? One approach is to observe that our 567 result holds for graphs with vanishing edge probabilities. So what I mean by this, I mean, if you tell me that all the edge values of the graph are very small, then it's easy to adapt our analysis to argue that this 567 selection guarantee is attainable, even if the graph happened to have odd length cycles. Good. So because of this, it suffices to argue that for designing an RCRS, the hardest setting is actually when the graph has vanishing edge values. And there's sort of some reason to believe that this is the case. For instance, our negative result of the upper, like the 567 upper bound, is for a graph that fits into this vanishing setting. This is actually a more significant problem, open problem in the literature, as also in offline contention resolution as well as edge arrival contention resolution. A lot of the time, it's possible to derive improved sort of selection guarantees, assuming one makes this vanishing edge value assumption. And so if one could show that this is sort of the hardest setting, then it would actually lead to tight selection guarantees in a number of other settings as well. Okay, so I think that I'll stop there. So thank you for listening.